Hi everyone. Welcome to today's webinar. We'd like to begin today's webcast by saying a big thank you to MemSQL for sponsoring our event, and we'd like to let you all know MemSQL is a data warehouse built for real-time analytics. Thank you again, MemSQL. Folks, I'm Yasmina Greco. I'm with O'Reilly Media, and I'll be your facilitator for today's webinar. Folks, joining us today, we have Mike Boyarsky with us, and he is going to talk to you about machines and the magic of fast learning. Mike is a senior director at MemSQL. His experience spans enterprise data solutions, including analytics and database software platforms. Mike is a veteran of the data and analytics space, having worked at Oracle and TIBCO before joining MemSQL. Folks, we're really excited to have Mike with us today to present this webcast, and I'll turn the program over to him in just a moment. But first, I'd like to go over just a little housekeeping to help you get the most out of today's webcast. You can submit questions at any time via your Q&A widget. It's located right down there towards the bottom of your screen. It says Q&A. Click on that. It'll open and submit your questions at any time for Mike. You can also open, move, and resize any of the other widgets. We also want to let you know that we're recording today's webinar, and we'll have the recording ready usually within 48 hours. And folks, it's my pleasure to turn the webcast over to Mike for his presentation. Let's welcome Mike Boyarsky. Hi, Mike.
Hello, good morning, good afternoon, everyone. Thank you for attending today's session. We've got a pretty exciting topic to cover today. We're calling this Machines and the Magic of Fast Learning. We'll go through the agenda real quickly. First, we're going to talk a little bit about real-time machine learning and some assumptions. Not every machine learning application is appropriate for a real-time workload, and so we're going to talk about and walk through some of those assumptions to help you as a potential developer or data scientist to determine what opportunities are ripe for real-time. We'll go through some example scenarios. Some of these are real customers through our experience. These have been anonymized in most cases just to give you a sense of the workload, the use case, and the scenario that this particular real-time machine learning application is in place. We also have some time for a demonstration. We'll highlight some exciting new capabilities that are part of our offering and go through those in a live demonstration. And then, of course, with time, we'll be able to spend some moments on the Q&A. If you do have questions as we go through, I'd recommend submitting those as they come up. Waiting till the end usually means that we may not get to all of those questions. To give you a little bit of context for those that are either new to MemSQL or just to give you a sense of where and what our position is in the realm of machine learning, we are a database platform. We are a relational database that offers the opportunity for businesses to become real-time enterprises. We are focused on delivering real-time processing of data through a full relational SQL-based database. Our product has been ranked by a number of industry analysts as being a very high performance, strong capabilities around operational data warehousing use cases and workloads. Ultimately, what we are looking to offer is the ability to be able to learn and act in real time. We have been founded based on a couple of our co-founders were from Facebook and a SQL Server database engineering team. We've been funded from top-tier investors, and of course we have a number of marquee customers and logos that we're very, very proud of. So that gives you a little bit of sense of who we are, and now we'll get into the topic of today, which is around how to take your data corpus, your data that's sitting inside your organization, that's growing in size and complexity, and taking advantage of that for machine learning applications. Most of these data corpus, in the evolution of this corpus, is driven through applications. These applications are typically used by, we call them actors for the purposes of this presentation. These are the folks that are interacting with these applications, generating data. In some cases, that data is stored in relational databases or other database systems. These applications also allow data scientists, who we are calling operators, the ability to sift through and identify insights, opportunities, and predictions that can be gained from this data corpus. Typically, these two roles, the actors and operators, work in sort of a batch mode process. This means that these two boxes, if you will, are they're integrated, but typically they're not integrated in any sort of real-time fashion. And this introduces a new exciting realm, which is the introduction of combining actors and operators into a real-time machine learning application. And so this is the ultimate, we think, opportunity, which is taking advantage of some of the new systems, the new processing capabilities, the new hardware environments and configurations to process data as it comes in and allow the data scientists community as well as the application users or actors to work together in a seamless, more real-time fashion. And so that's sort of the crux of what this talk will be going through. And so first, we need to go through some assumptions. This of course, turns the feedback loop on when we get into this real-time machine learning environment. Some of the assumptions that we must make to begin talking about, getting into the nuts and bolts of machine learning applications is that not all machine learning applications or workflows are appropriate for real-time. So at first, we have to talk about the fact that there are supervised learning models and unsupervised learning models. For the purposes of today's discussion, we'll be talking about with the assumption of those applications that can work with supervised learning, which is typically driven by regression or classification models. For those that might be new to these topics, regression models are typically based or used to predict continuous values that are presented or based on an assumed or a known output value. So for example, if I want to predict the price of a car that I'm trying to sell, I can input values that are based on the age of the car, maybe the quality of the car, maybe some of the add-ons of the car, and that will allow my model to predict the value of that car. The other type, which is classification, which is a popular model used for, or learning model used for image recognition. And this is where I want to classify an image, whether it's a person or another object like a physical object. And that sort of classification model, again, is typically used for those types of applications. Unsupervised learning is typically when you get into true, what we would consider the neural network side of machine learning, which is where the machine itself has very little inputs. It is going to actually generate those inputs and classifications on its own with no preconceived definition of what the data is. So again, real-time does require, a real-time machine learning application does require supervised learning attributes. I thought this quote was interesting, just to set some context. The fact that humans can typically create 1 or 2 good models a week, machine learning can create thousands of models a week. Now, creating lots of models may be good or bad depending on your use case, and in many cases it depends on what the scenario is. We think that there's a trade-off typically, especially when we're talking about real-time machine learning, which is the difference between the accuracy of the model and the latency of the model. In some cases, good enough in getting a model that is close enough to help you make a decision or predict a particular situation may be appropriate based on the application it's supporting. So for example, if you're in a fraud or advertising scenario where every millisecond may count and dollars can be gained or lost, that is an application type that is much more ripe for a machine learning use case. Whereas maybe a maintenance machine model for heavy equipment, capital intensive equipment, and or inventory management where the data may not be changing as frequently, and the accuracy of the model may deem to be more important to be high. That is also a trade-off that you need to make. So accuracy versus latency is an assumption that we have to make when determining whether it's appropriate for real time. So we want to look at those models, those applications where latency, speed, and response time is quantified or associated to opportunity in terms of money, cost, etc. So when you look at the supervised machine learning process, this is something that's been very well defined. This is just one representation or example where you have training data that comes into your environment. You may prepare that data, clean it, deduplicate it, something I'm sure most of those in the audience that are data scientists know. You spend most of your time in the preparation process. Once you get through that step and the data is prepared, you will then identify feature extractions. You will look at labels of the data and assign labels of the data to determine what are the trends that you're looking for. This helps reduce the dimensionality of the data. This helps you identify ultimately what it is that you're going to be measuring. And then once you get through this feature extraction process, then you will then run your learning model. You'll let the machine do the magic in terms of identifying what the appropriate result or model should be. And this process typically can take, depending on the size of data and the complexity of the data, dimensionality of the data, this could take from minutes to hours to days. And then once you get past that process of defining your model, then you get into the fun part, which is actually putting it into identification of a score or prediction. And that prediction can be tested to determine its accuracy. And this is where we get into a very common scenario with machine learning, which is the ongoing verification and testing and training of models to improve their accuracy, based on maybe changes in the data itself, maybe changes in the conditions, changes on feedback that are perceived from the application. Most of this process is done in some form of offline mode, which is that the training and the learning and the improvement of the model is an iterative process, and it takes, in some cases, days, hours to perform. As we get into the opportunity and looking at real time for supervised machine learning, this is where we see an opportunity where a more streamlined process can emerge. This streamlined process, of course, can plug into your existing batch-oriented machine learning process workflow that I just described, where the score is then inserted into your application as a particular SQL statement or application function, or what we see as something that's an emerging and yet a new assumption is the ability to actually eliminate or reduce the reliance on the ongoing learning and training process that's part of your application, and essentially translate that model directly into your database as a function. This is what we're calling the database as the model scenario. And this is, again, sort of a new exciting application type that we're seeing in some of our customers. We'll talk through one of them in just a moment, where with the advent of a ultra-fast query processing algorithm, the ability to extend the functions of the database so that you can insert essentially linear algebra into your SQL syntax, and to be able to process transactions in the same application or same database, you can get to a much more streamlined process, which again eliminates some of the batch-oriented workloads that are part of traditional machine learning applications. So this very fast flow or workflow is something that, of course, is determined based on the type of application that you're supporting and the complexity of the data that you're working with. And it also assumes that you have a very fast database that can process these types of calculations, these queries, in an appropriate window of time. So we'll talk a little bit about how some of this can be achieved by looking at some of the data ingestion and persistence layer of your machine learning stack. When you look at this diagram here, what you see on the left is the data ingest process. This is how you acquire your data. Typically, we see within the MemSQL ecosystem, a lot of our customers are using Kafka as a way to ingest data in real time. In many cases, they're also using Spark next to Kafka to help transform that data, prepare it, or do some sort of additional calculations of the data before it lands into the MemSQL database. The beauty of the MemSQL architecture is that we can ingest data directly from a Kafka topic or a Spark stream and land that data, structure that data into a relational database. And because it's a relational database, it gives us the advantages of providing SQL syntax. The SQL syntax is ANSI-based, and therefore you can ultimately run a number of analytic queries against that data. We do leverage an in-memory architecture, so that means when the data comes in through the ingest environment, it is doing that through an in-memory row store engine. And then we also move that data into a column store engine that's highly compressed for long-term and or historical analysis. So essentially, MemSQL is serving as a multi-model database in one complete system. And then once in the database, then you can run and write your applications, your application logic, and deliver your real-time dashboards and or deliver a real-time application through custom APIs. We do work with a number of machine learning tools, whether that's TensorFlow or Python, R, or MATLAB. We do have customers that take advantage of most of these modeling environments. That is something that is sort of integrated, decoupled from the MemSQL database, but we do work with these tools to help data scientists model and identify scores that can then be inserted or used in the MemSQL database. We are focused on a real-time workload. So today's emphasis today is on the ability to eliminate batch-based processes at the point of ingestion as well as at the point of extraction or query processing. So we're really focused on operational-based analytics as well as real-time machine learning use cases. It is a SQL-based application, so that means everything is ANSI-based. We do span our data from memory and disk, so it is a dual sort of mode database. And we also are delivered on premises as well as a managed service, so we can span from your local environment to the cloud seamlessly. So now we're going to transition real quick into some examples. These are real workloads that we have supported over the last few years as customers. So first we're going to talk about an exciting scenario with Thorn. Thorn is a nonprofit organization that's focused on defending children against exploitation, and it is a very data-intensive workload. They ingest a number of images on a daily basis. About roughly 100,000 new images are processed by the Thorn application. Ultimately, what they're looking to do is identify children that are being exploited and or put at risk. And through this process, they've identified a number of ways to detect and identify images on the dark web and process those images in a very fast and efficient manner so that they can hand that insight off to the authorities to help save and protect these children. Part of the application does involve a machine learning algorithm that helps identify vectors for facial recognition. Part of this is using the supervised classification process. These vectors are then used, and these vectors exist at up to about almost 5,000 different unique points. So it's a very large, sort of complex string, if you will, that is then used to classify and dedupe and match these images with a reference store that they have. The process is very complex in that they have already hundreds of millions of images within their database. So they're matching, if you think about the number of new images that are coming in, to a growing list of millions upon millions of other reference images. So it's a very complex matching process that they have to run and calculate. They were working on a workflow that was allowing them to process these images on the order of many minutes. It was taking them several minutes per image, and they found them the workflow of their application was backing up, which meant they couldn't get to all the new images that were coming in, and therefore they were feeling that they weren't able to cover all the opportunities or uncover all the opportunities in the data that they were getting. So what we ended up doing is helping them through an extension within our database platform to allow for what's called a DotProduct extension, which allowed for a much more fast and efficient processing of the Euclidean measurement point calculation. And what this did was it allowed for them to do the matching process in a much more efficient manner. They were able to actually improve the matching process by up to about 1,000x. And what this allowed them to do is to get through and process all those images that were coming in and ultimately identify more opportunities, more exploitation issues. A little bit into the Perforce scenario of their workflow that they used. They had this sort of high-level architecture in place where new images were coming into a image reference store in HDFS. Those images were then modeled using a TensorFlow application. Those models were then run in a custom application that they wrote and supported a custom user interface for authorities to interact and scan through images. With the new architecture, they took advantage of Kafka as a way to ingest data more efficiently, more quickly, ingesting that directly into the reference image store, as well as the MemSQL data store. We were able to essentially take these vector images, put them into MemSQL, and then run our dot product calculation, which was the essentially high-speed vector algebra. Ultimately, we were able to speed this process down by eliminating some of the training, learning, etc., and we've sped up the process matching dramatically. Another use case that we've seen take advantage of real-time machine learning is in the ad tech space, where you've got a number of users interacting with ads and you want to identify the most appropriate ad for that opportunity. The best ads are ultimately the ones that are going to convert, and this optimization path was used with Kafka as the ingestion engine, Spark as the machine learning algorithm modeling environment, and then ultimately the score was put into MemSQL, and MemSQL was used to score new interactions that were taking place on the data. We also see opportunities in the area of IoT. We have a customer in the energy space that has a drill environment that they're looking to essentially improve the uptime of the drill bits as the drills are being used. They're collecting information about the vibration, the speed, the direction of the bit, and are able to calculate potential failures before they occur. These drill bits are very expensive to replace. They're also responsible if they do break long-term outages take place, and that's something that ultimately they're trying to eliminate. So they were able to build or actually inject an existing model, a PMML model based on a SAS application, inject that into MemSQL using the Spark integration environment that we have, and that the whole workflow allowed them to respond to issues that may occur within minutes to seconds. So this again was a real-time application that allowed their drilling process to maintain a more significant uptime and reduce outages and cost. And so this is something again where the use case was really dependent on the speed and the detection of the issue, and it was based on an existing model that was already put in place by another application using SAS. At this point, I'm going to hand it over to my colleague Eric, and he's going to walk you all through another exciting example, more detailed example about that Thorn use case that I talked about. And so, Eric, would you like to take it away?
Yes, thank you, Mike. Can you hear me okay?
We can.
Okay. All right. Okay, so I'd like to, carrying on from what Mike mentioned about the Thorn use case where we're doing real-time face image matching. So I wanted to talk a little bit about the technology behind that we've added to MemSQL. So Thorn is using a representation of a face image, which is a vector of floating point numbers. So in our tests, we're using a vector of about 512 floating point numbers to represent an image. So the images have been pre-processed into these vectors, and these vectors have been stored into a MemSQL database as representations of the images themselves that are suitable for matching. And so Thorn has a database of a couple 100,000 face images of children who have been exploited or trafficked, and they're trying to take, as new images are come in, they're trying to match the images of missing kids against those new images, and they want to do that as quickly as possible so that applications that allow people to browse this image data and see potential matches are highly interactive and easy, and have a good user experience. So at the crux of this matching process is a vector dot product operation, which just takes two vectors and it multiplies the elements pairwise and sums up the products. That's what a vector dot product is. And so what we've done is, in an experimental version of MemSQL, is to create a new vector dot function which takes the dot product to two vectors, and that's a fairly straightforward calculation. The problem is, how do you do it really, really fast to get that interactive matching against hundreds of thousands of faces to see which of those faces might match one new face that you've gotten from a new image that you've just gathered. And so one of our engineers developed an extremely high performance built-in function for doing vector dot product in MemSQL. Takes two arrays of floating point numbers that are represented as a var binary data type, and does the dot product. And the way our engineer achieved this tremendous speed up to make this incredibly fast was through the use of sort of a clever use of Intel AVX2 instructions. So AVX2 is what's called a single instruction multiple data, or SIMD, instruction set extension that in the last 3 to 4 years, most of the Intel processors that have been sold have this AVX2 extension. And through a combination of use of AVX2 and just sort of clever interleaving of instructions and loop unrolling, we were able to get about 3 order of magnitude speed up compared to sort of a more simplistic way of doing this vector dot product. And so we've actually got the ability to run a query that does face matching, and if you really calculate how many floating point operations it's doing during the query, it's doing about 2 gigaflops on a 4-core processor, which is just in a demonstration. We're not even trying to do it in, on a large cluster. So on my MacBook, which has 4 cores and an Intel Core i7, I'm able to get 2 gigaflops during query execution through the use of SIMD. Now, a little bit more about this Intel AVX2. So the AVX2 registers are 256 bits wide, and so they can hold 8 32-bit floating point numbers. And a 32-bit floating point number is called a single precision floating point. So we can do 8, by adding together 2 registers or multiplying 2 registers, we can do 8 32-bit floating point operations in a single instruction. So like in a single clock cycle, we can get, say, 8 floats done. So what does this do? What does this do for us? So Mike mentioned earlier this concept of having the data be the model. So in this Thorn use case, it's a little bit different than a classical machine learning algorithm where you train a model and then on sample data and then you use that to score. Really, every single face that comes in and is added to the face reference database has a separate representation as a vector, and we can alter our model in real time by merely inserting a new face into our database. And that, in essence, adds one new category to a categorization model instantaneously. And then if you want to match another image against the database, that can be done in sub-second time. So we can update our model and do a score or pattern match both in sub-second time. So now I'd like to switch to do a little demonstration. All right, I'm going to present my screen. Okay, so I got a memSQL command prompt here, and this isn't running on a big cluster. This is just running on a MacBook with 4 cores. So I have a table here. This is an oversimplified example, but I have a table that's got 2 columns. It's got an ID number, I, and a column V, which is a var binary 2100, which has in it vectors that represent face images. So we've created just a hypothetical data set here with 200,000 rows. So you can see there, as I counted up the rows in that table, there's 200,000 rows that I've shown. So it looks kind of like gibberish there. I just pulled out the top, the first row, and you can see it's in binary format, so it doesn't print nicely, but it's just that's a vector. So now I've got here in another screen. Let me show you this query. So this, what this query does is it says, find me the top 5 matches to this particular face vector. So that huge chunk of hexadecimal, sorry, you don't have to read it, but just look at the top line. It's just selecting the ID number and the dot product of that particular face vector with the V column of this table X, which is the column that contains the vectors to match against. So X has 200,000 rows, and we're renaming the dot product calculation as D, and there's a filter there that says we're only interested in D values greater than 0.75, and we want to limit to only the top 5 matches ordered by that match calculation, which is represented as D in descending order. So let's go back and run that. Okay, so I'm going to run this match calculation against these 200,000 face images, and don't blink. Okay, so it took 17/100ths of a second. Okay, there it comes. It took 17/100ths of a second to run that calculation. What that did is it matched that face vector in the query against all 200,000 face vectors, calculated a score for each one, and then did a top sort where it sorted them out to pick out the top 5. So you can see number 1 is by far, has a 99.9% match. So that one is the top candidate, and then there's a few others that have a somewhat high score but are not even close to the top 1. All right. Okay, so that's it for the quick demo, but the thing that's really to note is, wow, a dramatic performance for doing a very complex calculation in a database to do that image matching, which is far beyond what you typically think of doing in a database. And imagine doing this on a cluster. We could match tens of millions of images in a fraction of a second with this kind of technology. So for applications like fingerprint matching or any kind of face matching, this kind of technology is applicable. Okay. Now I want to switch back to my slides. And another thing that I wanted to talk about was, switching back from we talked about the sort of data is the model type situation that we have with Thorn, but going back to a more traditional machine learning approach where you take a bunch of training data, you create a model from the training data set, and then you use that model to score records, and you'd like to do that in the database with a database query. So I wanted to talk through sort of how that might look and talk about a new feature that we're adding in the 6.0 version of MemSQL called extensibility, which allows you to create user-defined functions and stored procedures and user-defined aggregate functions in MemSQL's data language, and that those could be useful to help you encode machine learning models that you've trained outside the database and use them inside the database in queries. So I just wanted to walk through this briefly with a really simple model of cluster analysis. So suppose you have a machine learning situation where you've got clusters of data in a two-dimensional space. Here's a really simplified version of that situation where we've just got two clusters, and we've plotted a line between those clusters that has been learned from the data. The coefficients of that linear equation have been learned from the data to maximize the separation of those two clusters. And you can generalize this to many more lines and multiple dimensions with planes separating clusters and so forth. And so they're linear models for cluster analysis that you can build from training data sets, and this is kind of the most simple use case of that, just easy to discuss. And well, so suppose that the line that we learn from this training data set that is used to separate the clusters is this y equals 0.5x plus 1. Now, how can we use that to score data in a database? So with the new MemSQL extensibility capability, we support Scalar user-defined functions. And so we could basically calculate that line equation in a user-defined function, and based on whether or not your point was above or below the line, we can return the appropriate cluster number. So if you look at that function, it just calculates the y value for specific x value for a point that you're trying to score, and then checks to see if it's above or below the line, and using that, it determines the appropriate cluster number and returns it. So yeah, this is a very simple user-defined function. The thing that's important to know about MemSQL with respect to extensibility is our built-in database extensibility language, which allows you to write Scalar user-defined functions like this, is completely compiled to machine code. So the engineers that we had working on this project worked on multiple compilers at Facebook and are real compiler experts and know how to build a compiler that takes advantage of the effectively. So stored procedure and function extension capabilities in other database products. Functionally, they're fairly capable. However, performance-wise, they tend to compile the code to a pseudocode that's interpreted rather than compiling it to machine code. So MemSQL user-defined functions like this are compiled to native code. So our benchmark for how good the compilation was not another database product, but it was a C compiler. So functions like this are usually within a factor of 2 or 3 in performance of compiled C code in the MemSQL database. So that allows us to do some neat things with scoring with user-defined functions in SQL. So here's an example. Suppose I had a table of points, and I've got an ID number for the points, the position of the point, the x and y coordinates, and associated with that point, I have some weight. And suppose I had a query where I wanted to, for example, find the average weight by cluster. So that query can be expressed in SQL with that user-defined function very conveniently with what you see there on the slide. And we just call the cluster function. We're grouping by the cluster ID that's returned from that function and computing the average weight. So very simple query, pretty easy to write, pretty easy to understand. I didn't have to embed that crazy linear equation into my query, which I might have done if these user-defined functions were either not available or if they were too slow. And another example, suppose I wanted to find the cluster of point number 100. There's another example of how you could use that cluster function that was created in MemSQL's data extensibility language from a model that had been trained from a training data set. That's all I have, Mike. You want to take over?
Yeah, great. Thanks, Eric. So we're getting close to our Q&A session. Just before we get there, just to highlight the fact that we do have a book on the O'Reilly website. It's available at memsql.com/O'ReillyML, talking about the path to predictive analytics and machine learning. Really good resource for you to learn more examples, more use cases like we talked about today. So at this point, we're going to move on to our Q&A portion. So we do have a number of questions to get through. So we'll start with some of the early ones here. So the first question being, maybe Eric will start you off with this one. How can I connect R to MemSQL?
Sure. So R has the ability to connect to multiple different databases, and you can sort of put and get data frames from R to a database. And MemSQL uses the same connectivity protocols as MySQL. So one of the nice things about MemSQL is we have a very broad base of external applications that can connect to it directly because of this compatibility that we've created with MySQL. So you can, using the connectivity capabilities to connect to a relational database, you can specify MySQL and connect directly to MemSQL, and you can put and get data frames between R and MemSQL.
Okay, great. We've got another question here, and I'll start with the answer, and Eric, if you want to supplement, feel free. The question is there still a role for traditional ETL process? With some of the examples that we talked about today, there is an opportunity to eliminate and or reduce your reliance on ETL processes. It kind of depends on where and how many sources you're pulling from. But if you're able to, for example, pull from a single application or maybe a couple applications using something like a Kafka as your sort of aggregator processing, messaging environment, we do see customers that are able to perform some level of transformation using the Kafka to MemSQL environment, and therefore eliminating the need for any sort of ETL. ETL tends to be, under many environments, great for multi-sourced requirements. So you've got a number of databases that you need to merge, do some sort of cleaning, deduplication, and then it also tends to be more batch-oriented in those architectures. But we're seeing more and more customers moving away from your traditional ETL processes and going straight from, again, a Kafka or even a Spark ingestion, and transforming your data using the MemSQL environment because of the fast processing and SQL syntax. So that hopefully answers that question. Another question we got
to sort of add on to that. So, yeah, Mike, I think you're right on target. And there's some additional things I'm seeing with some of our customers where people are using MemSQL for real-time analytics, and they'll have maybe an archival data warehouse that's for data that's more than a day old, but they have sort of the real-time portion of their data warehouse or operational analytics application that has, say, the last day worth of data, and this can be extremely voluminous for some use cases, like in media and communications. There'll be billions of rows of data just from the last 24 hours, and customers are streaming that data into MemSQL, doing some enhancement and ETL or transformation of it, like streaming ETL with Kafka, as Mike said. And then they're able to do real-time analytics on, say, billions of rows of data from the last 24 hours and be able to, ask questions like, what are the top 5 most popular TV shows in the last 30 minutes, which is not a typical thing you'd be able to ask from a OLTP system that's just keeping track of who's watching what, or from a data warehouse, because it's more like a real-time data warehouse application. Then they take that data from the last 24 hours and they do clean it up and summarize it a little bit to save it off into an archival data store, either in MemSQL for long-term analysis or in another product. So that is sort of they're able to use SQL and use the parallel capabilities of MemSQL to do some final transformation to the data, sort of end-of-day data then that's sort of an ETL process or ELT process where they've loaded data into a database, MemSQL, and then used the SQL to transform and clean.
Great, thanks, Eric. All right, we'll keep going. Another question we have here is, can MemSQL replace technologies like HBase and or Cassandra? And maybe just a comment about how we work with Hadoop. So again, I'll start here, and then Eric, if you want to add anything. So we do see a similar performance characteristics in terms of ingestion, in terms of sort of reliability to the Cassandra and or HBase environments. Again, we have a very fast ingestion architecture. It's completely distributed architecture, so it allows for you to add nodes. If the streams increase, you can do parallel processing of the ingestion. So you can get to a very high level of ingestion. We have some customers doing 10 million upserts per second, and putting that into a structured relational format. And there's where the distinction happens between Cassandra and an HBase, and that we are a relational database. We are like a Postgres, a MySQL, and Oracle SQL Server, in that we have relational structure of data, but we can ingest the data very, very rapidly, store it in a relational format, and then query that data equally as fast. So because it's structured, because it's SQL, we can do very good, powerful analytics. That's something that HBase and Cassandra will have challenges for certain types of analytic applications where you want to do more advanced trend analysis, you want to do more historical reporting. Just doing reporting on a NoSQL layer, tends to be challenging depending on the type of analytics that you're doing. So that's where the distinction is that we believe in SQL. We're a SQL first database, but we do provide the characteristics of NoSQL in terms of ingestion. But we also are able to, in terms of working with Hadoop, take data, ingest data from HDFS. We can do that through our ability to load data from a variety of sources. So at the moment, we do not necessarily process queries directly on top of HDFS. We do need to ingest the data into MemSQL to run our queries, to process the data. But we do work with, and we do have customers that do have Lambda architectures where they might land data in HDFS, and then we will ingest the data from HDFS or directly from the application, or a combination of both. So that hopefully explains the question there. Another question we have is about the cloud.
I'd like
and whether
can I add a little bit to that last question about using NoSQL compared to MemSQL? So
absolutely.
So people that have NoSQL stores have some strengths, but they also have some weaknesses. I mean, they're kind of programmer friendly, but you can get yourself into a deep hole with these products because when you need to do some sort of structured query processing, the SQL capabilities that are available with these products are kind of weak. The query optimizers aren't that great. The performance is order of magnitude, even 2 orders of magnitude worse than a high performance SQL data store on similar queries. The capabilities for integrity constraints and so forth are not what you might find in an SQL data store. So, people that have grown up used to using SQL data stores, but have been tempted to consider using these NoSQL systems, it's a really good idea to take a look at MemSQL, because we can give you a lot of the virtues of these NoSQL stores in terms of scalability and performance, elasticity, but at the same time, as Mike was saying, you've got the benefits of SQL and everything that goes with that, the whole tool set, the query optimizer, very high performance query execution that could be a couple orders of magnitude faster than what you get in a NoSQL store, or you might be able to use just a lot less hardware than you're using to do the same kind of workload with a NoSQL product. Thanks.
Okay, great. And we'll wrap it up with one final question here as we get to the top of the hour. The question was around, the clarification on using MemSQL to train models. Is that what we are intending or describing in today's session? So Eric, maybe if you wanted to sort of clarify or explain sort of what our position is on using MemSQL for model training.
So with respect to model training, we talked about the sort of the databases, the model kind of scenario and so there, I mean, the model, it's not really a classic training proposition. We're just updating the model by just adding data. So in a loose sense, we're training real time. But most likely, though, I think most typically we'll see people do scoring in MemSQL using query expressions or user-defined functions, and the models will be trained in external tools. Now, there is one situation where, let's see. So there is a situation where, which may be useful to some people. Now, we do have new capability coming in our next major release to do, sorry about that. So we have capability in our next major release to have user-defined aggregate functions. So those aggregates can be used to create summaries of data like covariance matrices or whatever that could be exported and used in a training process. That's all I have there.
Okay, great. Well, that concludes our session today. I want to thank everybody for attending. And as you were told in the beginning, you'll get a link to today's recording. By all means, if you have additional questions, you can go to memsql.com and click the Contact Us button, and we can answer additional questions there. That's it for today. Have a good one. Take care. Bye.
Great. Folks, and on behalf of O'Reilly Media, we'd like to say a very big thank you to Mike for being with us today and for sharing all his knowledge and expertise. Thank you so much, Mike.
Thank you. Bye now.
Great. And Eric, thank you for the demo. And folks, we appreciate your time for attending today. And as we close out, we just want to remind you that MemSQL is a data warehouse built for real-time analytics. Thank you again to MemSQL for sponsoring our webcast. This will conclude our event. Goodbye, everyone.